Thank you. So, yeah, so RAG was already introduced, but maybe let's just quickly do it again. So, keyword search have been used for a long time, and BM25 works pretty well. But the appeal of vector search is that it can capture the context and the semantics of the questions. And in RAG, it's very useful because, well, people usually just dump the user query directly into the vector search, and then they get the relevant documents. So here I'm going to talk about, how you can improve the relevancy of those models. So why do you need the R in RAG? So RAG, if you ask GPT, it says, okay, it's called retrieval augmented generation, and basically you retrieve some documents, and then you dump that into the LLM, and then you get an answer. But what if you ask something like, what is the Zeta alpha architecture? And it will say, it's something like what is it, like a superhero or something? Clearly not right yet. And the reason is because LLMs know about public data, but not about your own data. So the typical flow is that you retrieve the 10 links, then you send it to the LLM, and the LLM comes back with an answer, and then you ask again, and then you get the answer, right? But provided that you gave the correct documents first. So this is an example of, the question is, what is in parse? And one of the documents says, what is in it for me? And the other one is the InPros 2022 release. Okay, and the answer is, I don't know, because it's not mentioned there, right? Then we ask again, a different system, and then, okay, it has the in-parse toolkit paper, and then answers correctly. One of those was using vector search, the other one was using keyword. Can you guess which one is which? Yes. So why is it so bad? Well, it's because this model doesn't know in parse, right? So it didn't find the correct tokens. And this is what can happen usually when you have some domain that the model was not trained on, because usually these models are trained on public data. So to solve that, you could, for example, create more complicated pipelines. So instead of just having the 10 links and then send that to the LM, you can do something like a tool selection, which maybe then rewrites the query, send it to two retrievers, KNN and keyword, then do the rank fusion to combine the list, then pass it to a cross-encoder, or LTR, and then back the answer. Or maybe there is even like an external service, some company-built API that has something to do with the answer. Okay, but if you want to, stick with the KNN or vector search, how can you improve it? So the answer is a fine-tuning. So the objective of fine-tuning is that you want to reshape the vector space such that the relevant documents are close to the query, and the irrelevant documents are far away from the query. The secondary objective is that you want it to understand your domain terminology. The problem is that to train the model, you need data, right? You need pairs of documents and queries. And of course, collecting queries is very hard, right? Because it's not that you're going to go to a company and they will have 10,000 query document pairs. But the idea is, why don't we generate these queries from the documents themselves using NLMs before the fine-tuning process? And so this is something called in-parse, which is basically that. You take a part of the document, you ask the LLM to create a query, and then that's it. And this is actually a paper that exists, so you can use it. It's open source as well. There's a toolkit for generating these synthetic queries. So then what you do with that is that you collect your training data. These are called positives. Positives means that you have the correct query matching the correct document, but you also want to give it some negatives so it knows what to get away from. This is a bit more tricky, but there are some techniques there. Then you select a base model, could be like multilingual E5 base. Then you dump all of the data through some scripts. Some magic happens, a lot of GPU hours later, or maybe not so much. And then you have the model that you can serve. And we have seen that it substantially improves the quality over kind of domain-specific data. In some of these cases, for example, this is a chemistry domain. We see that from the baseline, going to maybe baseline was maybe an older model. Then we went to A5, it improves a lot. Then we fine-tune it. We see that the blue line is German, improved even more. And then you can apply these other tricks that I mentioned, right? Like hybrid search, re-ranking, and so on, and you can keep going up and up. We also tried it with HR data, where it's a bit different use case, where you have, instead of query document, you have a CV and a job post. But we see the same result. The fine-tuning improves, as well as other domains like legal. But okay, E5. If you look at the leaderboards, E5 base is kind of old. So what about these newer models? So if you look at the MTAP, so MTAP is a benchmark that allows you to correlate how good models behave depending on different tasks. So if you look at the top 10, these are huge models, right? So these are 7 billion parameters, 30 gigs of VRAM, 4,000 dimensions. So it's going to be very expensive to run. But you see, it performs way better than the good old E5. So how can we actually, if you use these bigger models, how can we run them without breaking the bank? Because of course, if you have 4,000 dimensional embeddings, it's going to take a lot of RAM. So in in OpenSearch 2.17, it was added binary quantization, so you can take a lower precision of the vectors. And there is also disk-based vector search, which does some trickery to improve the recall of the search, even though the vectors have less precision. That is one way. The other way is called Matryoshka representation learning, where you train the model so that you can reduce the dimensionality of it, and you still retain some of the performance. And if you see the graph, you can see that when you are around 1 billion scale, it's going to take 20 terabytes of RAM if you don't do anything, right? So there is something that you need to do for sure to run it. On the other hand, well, as I mentioned before, these models need 30 gigs of VRAM. What if you are GPU poor, like most people? Well, you can also quantize the model weights. And you can lower precision, and you can see that the VRAM required to run the models then drops significantly. And then you can kind of correlate, how much VRAM does each of these accelerators have, and say, okay, maybe I have access to a Tesla T4, which is 16 gigs of RAM, and then you will, properly choose the correct precision. Okay, so at Zeta Alpha, we fine-tune models, right, as I showed you before, but the question was, can we take these bigger models and also fine-tune them, or is it too hard, or, what's going to happen? And it's very cool because in the leaderboard, most people post the recipes used for fine-tuning, but it's never exact, right? So you read it, and then you have questions, and then it's hard to answer, so we just had to do it again. And we took some inspiration. So we basically took this Mistral E5 7B as base. So we took some 30 benchmarks, datasets. We did some techniques with the negatives. And then we spent 80 hours of GPUs, around 1.2K. And then we achieved, we achieved the 8th position in the leaderboard, showing that indeed you can take some base model and then improve its performance as long as you choose the correct data set. And we spend about $1,000, so it's not so expensive. Of course, there is still some work to do, right? Because as I mentioned, this you cannot really run on a cheap hardware. But since we use this public information, we also are releasing the entire training recipe. So, okay, conclusion is that You need good retrieval for RAG. So vector search can work very well as long as the data domain overlaps with the training data of the model. Otherwise, you will need to fine tune it. And then using these larger models seems to be, the future. But they are still not very practical, right? So I guess you need to stay tuned for next. Some announcements. So we are at the booth. If you want one of our legendary mocks, as Eric can attest, please go have a check. And then we are also doing the Amsterdam meetup in November 14. So if you are over there or you know someone, feel free to join. Thank you.
Hi. With fine tuning, I think that there's a certain amount of lift you would get out of just solving the vocabulary, the missing vocabulary, right? But then there's a second problem. It comes with the questions that you're asking, and I think the vocabulary problem is kind of a no-brainer. You're just going to get that for free with fine tuning, but the asking the right questions I think is harder. So if you ask an LLM to come up with, give it a document and say, generate some questions for this document, unless it's learned how to ask the right questions, it's going to come up with some really dumb questions like, hey, what is an atom? What is a hydrogen? But if it knows more about the chemistry domain, it's going to ask smarter questions. So is there a certain amount of fine-tuning the questions that goes into getting better models?
Yeah, excellent question. Indeed, so when we work with a client, what we do first is try to get some user logs to understand how they search. Then we ask domain experts to try to think, okay, how would you like to search, right? Because maybe they search currently in a very keyword-based way, but imagine the future. And so we collect this, as much as possible, let's say 50, 100 kind of ideal question types. And then we ask the LLM to generate more of this type, and then, continue like this.